Alright, so what we want to do now in this video is introduce this topic of truth functions. What are we talking about when we talk about truth functions? Essentially what it amounts to is the truth value for some particular statement, some components of some compound statement, where there's at least one or more logical connective, right? Or something that's operating on that particular statement. So what this means is that the truth value of the compound proposition will be determined by the truth value of its components, right? So what we end up saying about the truth value for some parts of the compound statement will then determine the whole statement's truth value. And so what we will end up doing is composing or creating different truth tables that allows us to look at exhaustively what the different possible truth values are for each and every little part or component of some proposition, no matter how big or how complex it gets. And then that will help us determine what the truth value for any particular proposition is based upon the truth value of each of its parts, determining the truth value of the whole darn thing. Or another way to put that is the main logical connective, the main operator, if you want to put it that way. So once we know what the truth values are for each of the different components, then we will be able to say what the truth value is for the whole statement. So let's begin by just making sure that we understand the definition itself. What is the definition for truth functions? Right? Truth function basically just means any compound statement whose truth value is completely determined by the truth value of its components. Right, so we're looking for the truth value of an entire proposition, and we're going to need to do that by considering the truth value of each of the components of that proposition. All right, so previously we considered all the different logical connectives that we are going to use that will operate on the different atomic statements, or larger statements for that matter too. And so now that we have that basic grammar in place for this particular logical system, now that we have that explained, let's begin by assessing under what conditions various WOLFs, also known as well-formed formulas, will receive a truth value of true, meaning T, that's the symbol we'll use for that, and also under what conditions the WOLF will receive a false, which we will symbolize using an F. Something that's actually might be quite interesting for some of you folks if you're interested in computer programming or different languages for programming. What we have instead of T and F is going to be a 1 or a 0, meaning like on or off, yes or no, true or false. So essentially it amounts to the same sort of thing. So you might be able to apply that to other classes or other things that you do in life. But for our purposes, we're going to stick with using T for true and F for false. So we're going to start with a very basic sort of sentence, something that is not complex at all. So for instance, if A is the sentence that we're dealing with, and that's all we don't have anything else, then A will receive a T for true, and it will receive an F for false. All right, so that's pretty simple. If all we have is A, then it's either going to be true or it's going to be false. Nothing more to it, because for our purposes, truth is binary, right? It's either going to be true or it's false. We've already talked about how statements, for our purposes, are truth apt. It has to be either true or false. So if all we have is a single statement, A, then it's either true or false. Another way of putting that is the truth of A just is whatever it is. It's either T or F, true or false. But if A is true, then A's truth value is T. And if A is false, then A's truth value is F. These are the logical possibilities. It's exhaustive. And so if it's true, then the truth value is T. If it's false, its truth value is F. So that's pretty simple. But what we need to do is consider the truth value, how to figure that out for more complex statements. And in order to do that, we're going to look for what we're calling the main or the dominant operator. And essentially what that means is it's the main logical connective. It's the one that's sort of most important, if you want to put it that way. It's the one that its truth value is going to be determined by everything else. And its truth value is going to tell us what the truth value is for the whole entire compound statement. Or if you want to put it in terms of scope, the main or dominant operator is the one that will be widest in scope. That's why it applies to the whole entire proposition rather than just some of its parts. So on the handout, we're beginning with not be. Not be. So I'm using the tilde and it's being applied to the single atomic statement be. Well, we only have one to work with here, so we know that the main operator is the tilde right here. So that one's pretty simple. But now consider the following. Not G then B, or rather G then H. All right, so we've got two different operators here, two different logical connectives. Well, the horseshoe is not going to be the one that is widest in scope. The horseshoe, this conditional statement, only applies to the G and the H. And so essentially we're working within the parentheses first. And once we figure out this one, then we will be able to determine what the tilde is. So we have to work within the parentheses first because the conditional statement only applies to the G and the H. And then the tilde will negate that whole thing. So there, that's the one we use for the tilde there. All right, here's an even more complicated one. Not if A, or rather A if and only if F, and C if and only if G. So notice what I've done here. I've got two different statements that are within parentheses, and that's being conjoined together. But then I put these brackets around all of that in order to make it clear that the tilde is negating all of this stuff, everything that's within the brackets. And so I first want to work within the parentheses, so I'll do either one of these first, and then I'll do everything that's in the brackets, and then finally the main operator here is the tilde. So that's the one that's the truth value that I would figure out last based upon the truth values of everything else here. All right, so that's negation. What about conjunction? Let's look at that. All right, conjunction, the first example I've got here is K and not L. All right, so what is the main operator in this case? Well, it's not the negation, right? Because the negation is applying only to the L. And so essentially what I've got is the K is being conjoined to the not L. It's the conjunction, the dot, the and. That's the main operator. So we would have to figure out L first, and then the negation, and then K, and then finally the conjunction. And here is a little more complex example. We've got E and F, and not G or H. Well, notice that it's a little more complex, but also I've got two different examples, or two cases of the dot, the and conjunction. All right, so which one do I want to do first? Well, remember, we want to work from within the parentheses first. So first one I'm going to do is this one, E and F. And then I have to go over here and do G or H. And then I do the tilde. And then finally, this conjunction here is the last one that we do. That's the dominant or the main operator. It's the one that has the widest scope because it's applying to the whole entire statement, not just to a part of the statement like this one is here. And the reason why this tilde isn't done last is because this tilde is applying only to what's inside this parenthesis here, similar to what we saw previously, like this one right here. But notice that these can get much more complex, right? So here's a much more complex example, again, using the dot or the conjunction. So here I've got if R, then T, or S and U, and W if and only if X or Y if and only if Z. All right, so that's a much more complex statement. This is something I just created for the purpose of the handout. Again, we've got different cases of conjunction. And just like we saw up here, we're going to want to do this conjunction first because it's inside this parenthesis. And this is going to be the very last conjunction we do. Right? That's going to be the dominant operator, the logical connective that has the widest scope. It applies to all this other stuff. It applies to the entire proposition itself. All right, so we considered negation, we considered conjunction. Now let's consider disjunction, which again, remember, means or. This or that. So that's what we're going to look at now. All right, so moving on to disjunction, the first example I've got here says not C or not D. So remember the way that negation, the tilde works, is the tilde is only applying to the C here, and the tilde is only applying to the D here. Right? So that's totally fine because tilde is unary rather than binary. So we know that the or statement, that disjunction is the main operator. It's what's got the widest scope. It's applying to that whole entire proposition, not just to a single part of it. All right, so this example is a little more complex. Consider the following: F and H, or not K and not L. Again, the tildes are working sort of the same way up here, but now they're inside of the parentheses here. So we would want to do what's ever inside of this parenthesis first. We would also want to do what's inside of this parenthesis at some point, and then we would do the disjunct last, because this particular or statement, this or operator rather, is applying to the entire proposition here. It's the one that has the largest scope, is another way we put that. Okay, finally, let's see a much more complex case. Here we've got not S and T then U, or not X and Y if and only if Z. Again, this tilde here isn't applying to the whole thing. It's only applying to what's inside this bracket here. So we'd want to do what's inside the bracket, but first we'd have to want to do what's inside this particular parentheses. Likewise, same thing for this bracket. We would have to do the X, and we'd have to do the Y if and only if Z. These would have to be done first, and then we would do the tilde here. But again, we can see that the or is the main operator that's applying to all of them, to everything in the proposition. All right, so now let's consider conditional statements. All right, so for conditional statements, we're starting off with H, then J. So clearly, the only operator we have here is the horseshoe or the conditional, and so we know that that's going to be the main operator because it's the only one we have. But it can become much more complex. So if I've got A or C, then D and E, right? Again, this one, the horseshoe, is still the main operator. It's the one that we would do last. It's the one that has the widest scope. So we would have to do what's inside of these parentheses first, and then we would focus on what the truth value is for the horseshoe or the conditional statement. So you can kind of think about how really it's the same thing as what we have up here. It's just what's flanking the conditional, the horseshoe, is just more complex than what we have up here. But essentially the same point remains, right? We do what's on the both sides of the horseshoe first, and then we determine the truth value for the whole entire statement that way. But as we saw before, these can become very complex. So here's another example. K or S and T, then not F or M, then O. So on this case, notice that I do have two horseshoes, two different conditional statements, but this is the one that I would do last. right? So I would do this one first, and then I would do everything inside of this parentheses, and then I would have to come over here and do everything inside this parenthesis. And when I say do everything, what I mean is you'd have to figure out what the truth value is for all of those different variables, different components of the whole proposition. And then once I've done that, then I can determine what the truth value is for the main operator, which is this one here. It's the one that's widest in scope. It's the one that's that's being determined by everything else. And so that particular, that logical connective is the one that tells us what the truth value is for the whole entire proposition. Finally, let's look at how to consider the biconditional or the triple bar. So let's do that one. All right, so let's begin with a pretty simple one, like we've seen before, something like M if and only if not T. Well, even though that there's this negation, the tilde is in there, it's only applying to the T. It's not applying to anything else in the proposition. And so the triple bar, the biconditional, is being flanked by the M on one side and the not T on the other side. And so the triple bar here is going to be the dominant or the main operator that determines the truth value for the whole entire proposition. So let's look at a little more complicated one. I've got not B or D if and only if not A and C. So even though I've added more elements in here, it's essentially the same thing, right? I've got a negation that's applying to what's inside this parenthesis. I've got a negation that's being applied to this parenthesis, but it's the triple bar here that's the dominant or the main operator. So that's the one that we would do last. Its truth value will be determined by everything else. That's why we would have to do it first. But then it has the largest or the widest scope, so it tells us what the truth value is for the whole entire proposition. Finally, let's consider a much longer, more complicated example. K or F then I if and only if not L and G or H. Again, I'm just kind of making up examples here, but essentially the same thing applies, right? The truth value of the horseshoe is largest in scope, it's widest in scope, so it applies to the whole entire proposition. We would have to do everything else, figure out the truth value inside this parenthesis, left out a bracket here, figure out the truth value for that parenthesis, and then everything in the bracket, truth value for this parenthesis, then everything in the bracket. Then we could determine the truth value based upon everything else we've done for the triple bar, and that would tell us the truth value for the whole entire proposition. And so what we need to do now, I keep talking about determine the truth value, look at what the truth value is, try to figure out what the truth value is, but I haven't said anything about how to do that. So what we're going to do in the next video is we're going to turn first to understanding what the truth value is for each of the different logical connectives, right? All the different operators will have different ways of determining the truth value. And we're going to use truth tables to do that. Again, I want to go slow. I want to make sure that you understand these. So once we look at some of the basic sort of examples, then we can look at more complex examples. And that will put us in a position for next module where we'll look at how to determine whether or not some proposition is logically consistent. Maybe it's going to be self-undermining or contradictory. And we also will be able to use the truth tables in determining the truth value of all these propositions in order to understand and evaluate the validity of different arguments. So that's kind of the direction that we're moving in. So for the next video, let's start looking at truth tables.